We're having a look in this video at the representation of nuclei, the central part of atoms. The reason is that if we understand that, then we have a foundation for understanding what happens in stars in order to produce energy. So, representing nuclei. So the nucleus is this part of the atom, of course. Nuclei is plural and nucleus is singular. So we've got neutrons, first of all, and these are particles which don't have a charge. And we've got protons. In this particular case, we've got two protons, and we represent those by this letter Z. And when we write the symbol, or when we represent our protons, we put a little 2 down there. So that then is referred to as the atomic number. So the atomic number talks about the number of protons in the nucleus. Then we have this number here, and that number is called the mass number. And what that means is the total number of protons plus neutrons that are in the nucleus. Of course, that number of protons here also tells us the number of electrons, the negatively charged particles that are in the atom, that is, in the neutral atom. So in something like the periodic table, you might be familiar with this. You see numbers like this. Again, that is the atomic number, the number of protons. So it's 3 here in the case of lithium, and it's the number of protons that make it lithium. With 4 protons, we've got beryllium, and so on. So over here, if Z, the atomic number, is 8, that means that the atom is going to be oxygen. Now here is another way of representing the nucleus. What we've got is our total number of protons and neutrons, and that is as we've said, the mass number, and it's a whole number. Down here we see a new term, and this is the nucleon. All of these, or each one of these, is a nucleon. So a nucleon, as you can see there, is a general term used for both protons and neutrons. So we'd say a proton is a nucleon, a neutron is a nucleon. Isotopes. Now, isotopes are atoms which have the same atomic number, in other words, the number of protons, for example, carbon here. These 3 here are called isotopes. Carbon, this one here is carbon 12. And what that means is it's got 6 protons, that makes it carbon. It's got a mass number of 12, which would mean, of course, 6 from 12 gives us 6. It's got 6 neutrons. Over here, carbon 13, got 7 neutrons. Here, carbon 14, 8 neutrons. And we talk about this one here as carbon 12. Hydrogen is also another substance, another element which has isotopes. Most atoms tend to have some isotopes. In other words, the same number of protons here, this one here, normal hydrogen, has only got 1 proton. Of course it's only got 1 proton, that's what makes it hydrogen, and 1 electron. Here we've got 1 proton plus 1 neutron, and you can see here the number of nucleons. And this particular isotope has a name, it's called deuterium. That's how we'd say that, deuterium. Over here is a third isotope. These ones here, they're quite present in stars, in the formation of stars. Deuterium, normal hydrogen or protium. It's not very often called that, but we've got protium, deuterium, and tritium. So those are isotopes of hydrogen. We have radioactive atoms. And when we're talking about those, we're talking about atoms which emit some sort of radiation, particle, or in some instances it's a photon. Here, for example, we've got an alpha particle coming out of a nucleus, and they often call that alpha decay. Sometimes we can have a beta particle here, which is a fast-moving electron coming out of the atom, out of the nucleus. Now you might wonder, an electron coming out of a nucleus, aren't electrons around the outside? Yes, that's true. That's true. What happens here is what's shown down here. A neutron can actually break down, give out an electron, and that's where this is coming from, otherwise known as a beta particle, leaves behind a proton and can also give out some gamma radiation. At times we can also get another little particle which is known as a neutrino. Now you may not have heard of neutrinos. Neutrinos are almost massless. They are very, very small and light, but they're given out in massive, massive quantities by stars, and they were very, very hard to detect. They worked out that these things were coming out of nuclei in beta decay because there was a loss, or there was some mass that was unaccounted for in the whole of the nuclear reaction. Anyway, we don't have to worry too much about it, but there are particles called neutrinos. Over here is the last form of radiation that we can, or another form of radiation, and this is gamma rays, or a photon of a gamma ray. So the other term that we need to be aware of is atomic mass. Now, the atomic mass of an atom is different from its mass number. Mass numbers are always whole numbers. They're the number of protons plus neutrons. The atomic mass is the mass of an atom or of the nucleus compared with the mass of 1/12 of carbon-12. Now, to explain that a little further, if we have here the nucleus of the carbon atom, and we get 1/12 of that mass, we define that as one atomic mass unit. So, in a sense, this atomic mass unit is a comparison. We're comparing the mass of a nucleus with 1/12 of the carbon-12 atom. Now, the reason why it's done that way is rather complex to explain, and I won't go into it at this stage. So here is the definition. One atomic mass unit is 1/12 of the mass of C12. And it's not always a whole number. In fact, in most instances, it's not a whole number at all. Now, here we can actually see the mass of a proton in atomic mass units, AMU. Another letter that's used instead of AMU is simply U. And you can see here the mass of a proton is actually 1.007276 atomic mass units. One proton is more, it has a bigger mass than one atomic mass unit, a little bit bigger. The same thing goes here for a neutron. An electron, of course, has a mass, and that's its mass there in atomic mass units. Atomic mass units can be converted into kilograms, and up here you can see numbers which do that. So that's the number of kilograms for a proton. That's the mass of one neutron. That's the mass of an electron. Rather small, but there they are. And these figures here, they can be worked out to a very, very high level of accuracy with the machines that are available. Well, that puts us in, so this is just another illustration of the mass of a proton, the mass of a neutron. This is the charge on a proton. The electron, of course, has the same charge, but instead of being positive, of course, it's negative. So this gives you a picture of how we describe atoms that are in stars that collide. We'll talk about that later. These particles, particularly hydrogen, collide and form new substances, and this is a bit of a foundation for us in understanding what happens.